We're on types of compounds. Right now we've come off of talking about different kinds of bonding. So we had, what was the first kind? Do you remember?
Hydrogen bond.
Well, before covalent. We had a positive something, a negative something.
Chemical.
Ionic.
Oh, ionic.
Okay, so with ionic bonding, I've got a positively charged ion. What do we call those? Cations, and a negatively charged called anions, and a positive negative get too close, and you have this connection. Now, that's kind of a selfish bond because some atoms give away electrons, some steal, but basically they're doing that to make them self-stable. Okay. How is covalent different? That's what we talked about last time. For covalent, do we have giving and stealing? What's different? They're sharing. Okay, so I could share my electron and then I get it eventually back. And that creates a stronger bond. It's a lot tougher to break covalent bonds. And hydrogen bonds is what we just saw, where I've got this breaking, remaking, and it could also fall apart on its own. It's a very weak connection that can hold, boom, boom, boom. It can hold polar stuff together, but non-polar stuff don't have that. Did we talk about this?
Oh, no, you said you were talking about today.
Okay, so it's oil and water, and if you mix these, do they ever really, truly mix?
No, flip it.
No. Okay, so we could shake, 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 and if you've ever seen like Italian dressing, okay, Italian dressing is kind of the same thing. It's oil and water with some spices in it, and you have to shake it all up before you use it. It's mixed, but it doesn't want to stay mixed.
Not for long.
So what we've got is a whole bunch of polar stuff, which has those charges. Think of water. Let me go back to that part of the, go back to that. Okay, so water's polar, has this positive negative business. That makes it attracted to other polar things. So what you're seeing is all this water wants to be with other waters, polar stuff. What about the non-polar oil? Does it get included? No, it gets pushed out of the way. It doesn't have any of this positive negative business, and so it doesn't get attracted to the water. It actually gets repelled. So if you have greasy, yucky hands and you try to get all that grease off with just water, good luck, because it's not going to get the grease off. You have to use some soap or something else to get the grease to mix with the water.
More grease.
Okay, that's where you use something like gasoline, some sort of non-polar material to pull the polar away. Okay,
Go, Joe.
here we go. Oh, did you make it?
Boom.
All right,
Yeah,
nice.
I did.
All right, so we're up to some different kinds of compounds. Last time you built some wonderful looking things. You had some carbons and hydrogens and oxygens, and you built all these ball and spring models. I've got one here of glucose. What are the chances it's going to stay together? Okay, so is that a little more complicated? Yeah, a little bit. Okay, and so what we're going to be talking about today, there are some kinds of compounds that are a little bit different. Let's start with these two questions. You don't have to write these down unless you want to. What's the definition of a compound? Think back or look back. If you think compound, what does that mean?
Two things are
A
combined.
little bit more than that, Tyler. You've got a good start.
Two things that combine that make sense.
What are the things? Elements. All right, so two different elements combined, okay? Follow up. Why? Why do atoms form compounds? Why though? They want to fit together. Boom! Gold star, Tyler. Okay, so the overriding theme. The overriding theme is every atom wants to be stable. Okay, at whatever the cost. So some atoms become stable by giving away an electron or taking electrons. Some atoms become stable by connecting with other atoms with covalent bonds. But the overriding theme is, I want to be stable. I want to be a full valence. Okay? Keep that always in the back of your mind. All right, T-chart. In your notes, you should be writing some of these things down, guys. You'll forget it as soon as I say it. T-chart, if we take all the different compounds we could build, all the different compounds, some of them we built last time would go into the inorganic group, and some of the ones we built would go into the organic group. Every chemical in the world belongs in one of those two. Nothing exists in both. Okay, there has to be this separation. So we can take all the chemicals, all the compounds, and break them into two categories. Your job is to know what's the difference between the two. The way to do that, we look for some clues. There's clues that we can look for to tell us, all right, it's organic, it's inorganic. First clue, we look to see what it's made of. And this is pretty straightforward. If it's got carbon in the formula, if it's got C's, it is an organic compound. There are a couple that don't fit that rule, but most of that applies. Yeah, so if I see a formula, it's got some C's, it's got some H's, it's got some O's, it's got some whatever. Organic. Okay. Second one. Second clue is how it's held together. Well, organic is held together with covalent bonds. They like to share. I'm sharing an electron back and forth. Inorganic don't like to share. They like to give and take. They like to steal and donate. I think that one's easy. Inorganic starts with an I. Ionic starts with an I. That's pretty straightforward. Problem so far. Okay. Third difference. Inorganic tend to be less complex. We built a lot of these last time. H2O. O2, CO2. Okay, so these are pretty small. They're not super complex. They don't have a lot of atoms. Robert?
So an organic would always have carbon and inorganic always does not have carbon.
I didn't have the word always in there, but yeah.
Most of the time.
Yes. So the only one that doesn't fit that rule, Robert, is CO2 is technically inorganic. It doesn't really fit into some of the nice cozy patterns that we got. It does have carbon, but it's inorganic. And part of that is because look at how small it is. It's only 3 atoms. That is pretty inky-dinky. Okay. Huge, complex. That's like this one. Well, this is the smallest organic. All right, some of the biggest have thousands of atoms put together. All right, that we'll talk about. Okay, so just in this, we're up over 30 atoms. This has 3. Well, that's a pretty big difference. Okay, problems there. Fourth difference, last difference. Inorganic don't need to be made by living things. They can be, but these were here before life was on this planet. there were gases, there was water, there were inorganic compounds in the soil, in the air, in the rocks. They were here before life. Organic compounds, must be made by living things. So those only exist where there is life. Okay, look at these 4 differences. If you look at these 2 categories, inorganic, organic, which do you think we're going to focus more on? All right, I hear it both. Those that think organic, why? Why should we focus more on that side than the
Because
other?
we're in biology,
Which, take it one more step.
this stuff is living things.
Okay, so if I am trying to understand how living things work, I need to understand these compounds, because that's what's made by living things. This other side, it is important. Okay, it is important. These are important things. Water is a good example. Gosh darn, water is important to us. We're mostly water, but it's inorganic. Okay, so we're not going to focus a ton on these. We are going to focus the next week or so on these guys. Okay. Problems there, thoughts? Okay, so we're going to ignore the inorganic side. Okay? If you take chemistry next year, you will get plenty of that. Okay? Organic compounds. Now, as biologists, there are 4 groups. I think of these as like little subcategories. 4 types of organic compounds. We can put them into these 4 groups. Carbohydrates, lipids, proteins, nucleic acids. If you look at those 4, which ones sound familiar to you? Carbohydrates, proteins. Okay. I would guess you already have some understanding of what those 2 things are. Maybe not, but I would think you already know a little bit about those 2. Lipids, you might never have heard about. These are the fats. Okay. Nucleic acids, this is DNA and RNA. Those are our nucleic acids, which I'm sure you've heard of, but maybe don't know what DNA stands for.
It's already.
RNA is kind of like DNA, it's like a cousin. Okay, which we'll get to.
Not a
So
first cousin.
we're going to talk about these 3. Today we're going to focus on carbohydrates. Start with one that's kind of familiar, but we'll get to the other 3 the next week or 2. Okay, so we're going to zoom in. We started big, organic. We zoomed in on carbohydrates. Okay, now we're zooming in a little bit of what makes up these carbohydrates. Okay, start some basic stuff. First thing is they're really basic elements. Carbon, hydrogen, oxygen. Look at where these are on the table. Boom, boom, boom. Man, we're only in the first 2 energy levels. We're nowhere close to D's, we're nowhere close to F's. Simple. So that helps us out. Another cool thing about carbs is how many of things there are. There's a rule that you might want to know. The number of hydrogens is always double the number of oxygens. That's going to be handy to know. The number of hydrogens is always double the number of oxygens. So, if I had a formula and I only gave you that bit, how many O's are there going to be? always going to be half. Okay, so whatever way you want to think about it. Oxygen's half of hydrogen, hydrogen's double. Okay, I could give you any formula in the world. If that's true, and it's only got carbons, hydrogens, oxygens, your money is on carbohydrate. Okay. There is only one carbohydrate formula you need to know. It is the most important molecule in your body. It's called glucose.
Why is it the most important?
It's like sugar.
Thank you, Robert. The reason it's the most important, it's the only molecule your brain can use for energy. Pretty important. All right, so everything you eat, whether it's a Big Mac down to a tortilla shell, whether it's a greasy piece of pizza on Wednesday, okay, whatever, okay? The idea is every food product you eat has to be turned to glucose, otherwise your brain can't use it. Okay? C6H12O6, you need to memorize that, make sure you've got it.
I thought,
Because we're going to go through a lot of examples with glucose. Yeah, Brandon?
I thought only plants use glucose.
Plants can use glucose, they store glucose.
Yeah.
All right, but glucose is otherwise called blood sugar, or sugar in your blood. So if you're diabetic, you have a hard time regulating glucose levels. You have to check your glucose periodically throughout the day. Okay? Question on that? Okay. You probably already knew it, but in case you didn't, carbohydrates, the reason you need them, energy. Okay, if you choose not to eat a whole bunch of carbs, then you don't have enough energy. Yeah. Lane?
What if you have like 13 hydrogens?
Where?
Like, it's always half. What if you have like 13?
Ah, well, it wouldn't exist. That's a good question, though. Yeah, it's always going to be some even number. That's a good
So if you
question.
have 14, you have 7.
You got it. Okay, so it's based off of really this. Whatever the oxygen number is, it's always going to be double. So you could have an odd number here. Let's say it was 09. Well, then your H's would be 18. Okay, you could have something like that. Yeah. Awesome. Okay, thinking carbs. What kinds of foods have a lot of carbohydrates in them?
A lot of sugar.
Okay, like what? Give me some specific examples.
Bacon.
No. Bacon has almost no carbs at all.
I'm kidding. Cake.
Cakes. What else?
Chocolate ice cream.
Gummy worms. Oh man.
Gummy
I
worms.
love sour gummy
Sour Patch
worms.
Kids.
All right, so I'm going to put gummy worms / candy. So that takes care of all the different kinds of candy. Think of some other stuff.
A
high in
bowl of
carbs.
glucose.
Oh, come on. We don't have bowls of glucose.
Pancakes.
Ah!
Make one.
Pancakes are good for carbs.
Eggs. Jello.
Nope, no eggs.
No eggs. Jello. What?
Jello, no Jello.
Jello has sugar in it.
It does, but it's a better source of protein. Pops and sodas,
Ice cream.
you're missing the major ones though.
Pasta.
Pastas.
What's the major?
Pastas have a lot of carbs. What are some other?
Candy corn.
We got candy.
Bread.
Meat.
Breads.
Really?
Breads are very high in carbs. There's one more.
Granola.
Granolas, grains. I'm gonna expand that one a little bit, Brandon. Throw granola
Peanuts.
in there.
Would that
Not
be-
so much.
Would that be like
Cashews.
cereal or something?
Nuts in general have very little carbs. They have more
What about walnuts?
protein. More
They're
protein.
super.
You're thinking protein. Meats, eggs, dairy products, protein.
I said meat.
All right, so think of food pyramid.
Nice.
All right, carbs, breads, pastas, cereals,
What about
Vegetables,
natural
sugary
sugars?
stuff. Fruits and vegetables.
Oh, it's
Now, I think this is the kind of cool thing. So you guys came up with all this. You think of the big groups. Think about the stuff you like to eat.
We use a lot of carbs.
It's a lot of carbs. Okay, the American diet consists of about 80% carbs. Okay, you think of all the stuff you enjoy eating, it's probably somewhere in that list.
Notice how you said the American diet.
The American diet has a lot of carbs. Now, the thing that I think is good about that is, what are we using them for? Energy! So we're putting lots of energy into our body. That's the good thing. What's the bad thing?
You don't use them.
We may not use all that energy. So if we're putting lots of energy in, not using it, your body is programmed to store it. Store it. And the storage form of energy is fat, which we'll get into next week. So we're designed to prepare for famine.
For what?
The human body is designed to prepare for famine. So according to your body, famine is right around the corner. And your body is designed, if there's extra energy, store it, because famine's coming. Okay, famine never really comes, okay, so we just keep storing it. If we put too much energy in and you don't use it, you get it stored, and that's the problem. So you have to balance.
How would I put myself into famine? Stop eating.
Not eat.
All right, just moving forward.
But that gets into some dangerous territory, because some of these diets, and this is what we've been talking about in anatomy, my juniors and seniors, we've been talking about fad diets. What are fad diets?
Fat diet.
Fad diets.
Things people say.
Things people do for how long?
Oh, you.
A few weeks, a month. I need to lose 10 pounds so I can fit into this dress, fit into these pants, whatever, okay? And so we drop a lot of weight basically by starving ourselves, and then when we go back to eating normal, we just gain it right back, okay? Well, the idea is most of these diets have to do with cutting out carbs. If you cut out carbs, you're cutting out your number one source of energy, and so you force your body to do what it doesn't want to do, is use up the fat. It sounds good. The problem is it doesn't want to do that, and so after you lose some weight, your body actually holds on to it tighter because it wants to store it. And so you may lose a little weight, but then the rest of it gets harder and harder and harder to lose
Is that why it's so hard
because
to
your
lose
body
fat?
is wanting to hold on to it, hold on to it, hold on to it tighter and tighter and tighter. It's my little fat. I want to keep my fat.
Wait, is it that why it's so hard to lose fat?
Yeah, it's really hard to lose weight, especially large amounts of weight. Okay, especially after the first couple. I mean, if you watch Biggest Loser or any of those shows, they are working their tails off, okay, literally, to be able to lose that kind of weight. All right, we'll get into some of that next week, though. You guys are thinking ahead, though. All right, so on your paper, you've got a couple different kinds of carbohydrate. There's 3 groups. So we've gone from organic to carbs to certain kinds of carbs. So we're kind of narrowing our focus. Anybody want to try to pronounce that word? That looks horrible.
Monosaccharides?
Ooh, that's really close. Yeah, pronounce it like a sack. Monosaccharides. We don't pronounce the H, okay? If I look at this little prefix mono, what do you think that means?
One.
You guys are awesome. 1 molecule. Now, in terms of energy,
Do you write this down?
you're writing this down in notes still. Okay? Monosaccharides is our first group. It's only 1 molecule big. If we use carbs for energy, how much energy is this going to give me? It's 1 molecule.
Not much.
It's not going to give us much. Okay? Quick energy. But it's not going to last. It's not going to be very much. Okay. These tend to taste sweet. We call them our simple sugars. So anything that tastes sweet, we tend to like because it's going to give us energy. Your bodies are programmed to get energy by eating. So this is a great way to get energy. Eat something sweet.
What about like Energy drinks.
Energy drinks. Have you guys looked at the ingredients?
Lots and lots of sugar.
Well, there's sugar, there's water, there's caffeine. All right, the caffeine causes your body to basically metabolize sugar faster. So you're basically eating sugar water and burning it up fast
With a little bit of flavor.
with some flavor and some color and some cool marketing.
Cool.
Monster. And all these, 5-hour energy drinks and all these sorts of things. But it's basically sugar water with some caffeine to basically make you feel more energized because you're going to break apart all that sugar all at once. And so you get this nice burst of energy, and then what happens? You're used up. Okay, all that energy got used up and then crash. Okay, and then some people said, "Well, just drink another one." Okay, so boom, and then boom. All right, so you end up with this spikes and then plummets, and spikes and plummets. Okay, which, yeah, I suppose that could get you through a certain part where you need some energy, but that's not an overall good policy for life. Okay, all right, you've got some stuff cut out. Back to our paper. Monosaccharides. I want you to take one of your glucoses, just one of your glucoses, and glue it down in this monosaccharide spot. Okay, so take one of your glucose and glue it down. All right, so you should have now a glucose. Glucose, and you cut off a little OH. And then you should have another glucose that's combined to it. And I don't know, yours might be oriented, it might be oriented
Mine has to
different
be
than mine.
upside down.
It's okay.
What?
One might be upside down. It's
Wait, you want
okay.
us to glue this?
All right, once you've got those fit together, glue that down on the disaccharide spot. They should fit together like a puzzle. And if you look at it, your OH and H should be able to fit together too. And you want to glue that down too. Okay. So when you're done, hopefully yours looks better than what I've got on the board. You've got two glucoses stuck together, and you've got an OH, H stuck together. Yeah, you want to keep the little H. You're going to put that with your OH. Now, if you lost an H or somewhere along the line, you can draw it. You can draw it in, but I'll kind of walk around and see how we look. Yeah, one of them may be upside down. That's okay. Make sure it's the glucose. And let's make sure we've got what we have done. All right, so if you noticed, not all monosaccharides look the same, do they? The glucose and fructose, something looks kind of wacky. All right. That's because there's different shapes. So now we're back on those, kind of multitasking. We're multitasking. All right, some monosaccharides look like a hexagon. Well, that's because they have 6 carbons. And so when these carbons connect, they form a hexagon shape, like glucose. We call those hexose sugars. I think that kind of makes sense. Hexose, hexagon. Fructose, if you look at its shape, it's a pentagon. It's got 5 sides. That's because it's got 5 carbons. And so when you look at its shape, it looks different than glucose. But these are still both only 1 molecule big. Okay. What you just did, you built some disaccharides.
My paper looks pretty good.
Disaccharides, if you look at your paper, should have two monos put together, mono. We put two of them together. What did you have to remove to put them together? Water.
Could I go across the line and get a drink?
In just a second. All right. Get a little phrase down. Dehydration, synthesis. I think this makes perfect sense. If you are dehydrated, what does that mean?
You don't have enough water.
You don't have enough water. You've had water removed from your body. You removed some water. You dehydrated those chemicals. Synthesis means to make. I'm synthesizing. I'm making something new. Dehydration, synthesis. You took out water to put things together. Okay? So I look at it this way. You took an OH off of one and an H off of the other. That turns into water. You don't have to draw this unless you feel so inclined. Looks like a weird pair of glasses. Okay. You've got them on your paper actually stuck together. What's keeping them together is a little oxygen, which is holding their hands. Okay, problems there. All right, last one on your paper. Hopefully, you've got 3 glucoses left.
What? I have exactly that.
3 glucoses, your job is to put those together, but that is going to be called a polysaccharide. Well, it's more than 2. So polysaccharides are going to be our most complex group of carbohydrates. Figure out what do you need to remove.
You want us all three of these together?
Yeah, you want to put all 3 together. Think about what do you need to remove to put those 3 together.
I got this.
And then do it. This is the last step.
Ow.
Last step. 3 glucoses, stick them together.
Table.
You got to remove maybe a couple things this time.